Welcome back to the part C of lecture 12. In this video, we are going to start K-class classification. To understand the K-class classification, we are going to consider Irish flower dataset. It's an English flower, Irish, and it has three subspecies. One is Irish flower, Irish versicolor. Second is setosa, and the third is virginica. Now, obviously, this is the sepal, and this is the petal. This is the sepal, and this is the petal. Now, of the flower. So, what they have done, they have in this data set, they have taken the petal width and petal length, and then similarly sepal width and sepal length. So these are the values that are being collected for different flowers, and based on these flowers we have to say whether it's like, it's just how the data set looks like. For a particular flower, say sepal length is 5.1, sepal width is 3.5, and based on suppose setosa, and then we call it group 1. It belongs to group 1. We label it as a group 1. Similarly, there is another which has a sepal length of 7, sepal width of 3.2. You have petal length, you have a petal width, you have a petal length, petal width, and that belongs to versicolor, and we call it belongs to group 2. So that's how it's been collected. Now that's how the data looks like. So now our job is to classify these data, create a classification technique, and for a new data point, say this is a new data point. Okay, I don't know, suppose this is a new data point. Would you like to classify it as a setosa, or is it going to be a versicolor, or is it going to be a virginica? So for this new test point, and a flower which got these values, sepal length and sepal width, what kind of classification, which class you would put it? So suppose what we can do now, given the features of the species setosa, I can create a subset of the data. Similarly, given the feature of the subspecies versicolor, I can just create a subset of species of the data, and similarly I can create a subset of the data for where all the features, all the species are virginica. So we can assume that xk follows joint probability distribution with some PDA, probability density function fkx. Okay, now given a test point, we want to classify then new flower into one of the three species. Okay, so given a test point, which species it belongs to. So now you can imagine, given the species, I can try to think of these points. Blue points belongs to have their own probability distributions, which is setosa. The brown points, all the brown points which are virginica, have their own probability distribution, and the red points which are versicolor, it has its own distribution. And so I can think of this distribution, classify these distributions, and based on these distributions I can try to make a analysis. We call it discriminant analysis. Now suppose if kx is the class conditional density of x in class G equal to k. So that means if you go here and see that this a particular distribution, we will call it f1x. This is another distribution, we will call it f2x, and this is another distribution, the red one. So let me use a different color here. So it is f1x is the distribution of all the setosa, and then f2x is all class conditional distribution for versicolor. Okay, this is, and this is for virginica. Okay, virginica. Okay, now once you get this class conditional density, you suppose pi k be the prior probability distribution of class k, and sum of the pi k is 1. Then you just use Bayes theorem and you can compute probability of G equal to k given x. For new data point, I only know the x, I don't know which class it belongs. I'm just given the data point, can I compute the probability of that the point belongs to class k. That's just apply the Bayes theorem, fkx times pi k divided by sum of the flx pi l. In terms of ability to classify, having fkx is almost equivalent having quantity probability of G equal to k given x equal to x. So when we classify, so this point, if we want to classify, when we plug it in, what we found that the probability, the class conditional probability or Bayes probability is 0.861 for setosa, 0.029 for versicolor, and 0.110 for virginica. So this point belongs to virginica with probability 0.110. It belongs to versicolor with probability 0.029, and it belongs to setosa with probability 0.861. So most likely this point is setosa. So many techniques are there to model fkx. Now question is, how do I model fkx? There are many techniques are there to model fkx. Linear and quadratic discriminant analysis uses Gaussian density. One can use finite mixture models, one can use non-parametric density estimation models. A lot of models we can use, but in this course we will just assume Gaussian densities, and we will only keep ourselves within the linear and quadratic discriminant analysis. So you can try some advanced modeling, but for this first we will check linear discriminant analysis. So if you model class density as multivariate Gaussian, and then for each class, if you assume this particular thing, like for each class covariance matrix is same, this basically homoscedasticity assumption, then the resulting solution will be linear discriminant analysis. Okay, now so we want to suppose compare class two classes k and l. Let's look at the ratios. If you just look at the ratios, and you can see that this pi k and pi l is already known to us, and mu k, mu l, sigma inverse, these are all known to us. So these entire first two term is completely sort of a parameter driven. So you can write it as sort of a, this part is alpha, and then X transpose sigma inverse, this mu k minus mu L is sort of a X transpose beta kind of thing. So this is my beta. So you got, so this ratio you are writing it as a alpha plus X transpose beta. So this is why it's, this methodology is called linear discriminant analysis. Now if you do this linear discriminant analysis will give you a decision boundary between classes K and L, and these decision boundaries are turns out to be linear. We will see about it in few slides. And from the above linear discriminant analysis you can come up with the decision boundary like this, and base decision rule is just basically for each argmax of the delta kx. So this is the best decision boundary. So linear, for this particular linear discriminant analysis we came up with a sort of a, this was the, so anything in this region will be effectively on the Virginica. Linear discriminant analysis was giving us Virginica. This was versicolor, and this is Setosa. Okay, so that is linear discriminant analysis. In practice we do not know the parameters of the Gaussian distribution, so you need to estimate from the training data. So how you do that? Pi k, you can just take the frequency, like proportion of the data points that belongs to class K. Mu k is simply sample mean, and covariance matrix is simple sample covariance matrix. These estimates are all maximum likelihood estimates, so you can use it. So quadratic discriminant analysis is when, if you assume sigma k are not equal to sigma, and for each class you are going to compute the covariance matrix. At that time resulting solution will be QDA, or quadratic discriminant analysis, and decision boundary is slightly complicated but it is not impossible. Now what happens, you can handle it. I have taken this figure from Hesti and Tepshirani's book, James Witten Hesti and Tepshirani's book. So this is how the linear discriminant analysis looks like, and this is how the quadratic discriminant analysis looks like. So they are trying to model a 3-class problem like the one we are doing with the Irish dataset, and they showed that how a discriminant analysis will behave and how linear discriminant analysis will behave. The decision boundary is like quadratic in for QDA, and decision boundaries are linear in LDA. So thank you very much. See you in the next video with hands-on.